So with this our previous problem, Rankine cycle problem. So we have completed our module 1. So this is our second module now. So second module is completely dealing with the steam nozzles. So regarding these nozzles, generally compressible fluids and incompressible fluids will be using the nozzles. So incompressible fluid is either water. We can take it as an incompressible fluid. We might have seen in a fluid mechanics lab. Even in your previous course also, you might have done. You might have done experiment on venturimeter, finding a coefficient of discharge of venturimeter. You have done there. You might have seen the convergent divergent nozzle. So that is using a incompressible fluids. Now this module is completely dealing with the nozzles, which is using a compressible fluids, that is gases, vapors. Steam is a vapor there. So the basic content of this module is, so when the steam is allowed to pass through the nozzles, how the properties are changing, how the steam pressure, temperature and velocities are changing, and how you are getting the increased velocity at the outlet. So that with the help of a governing equations we can able to calculate. So accordingly, if I want to design a nozzles, so knowledge of this module is essential for us. By studying the various governing equations, we can able to design a steam nozzles with the knowledge of this module. So we'll be studying the basic equations of calculating the velocity of nozzle at exit and mass flow rate, so-called critical pressure ratio. These are all some of the equations or derivations we'll be getting it. And by using our steam tables, so we are going to solve the problems of steam nozzles. So these are all the complete content of this module now. So now let us before going to the theoretical part, so let us first understand the something about the nozzles. So nozzles are variable shaped device. So it is not a constant diameter. So it is a variable shape. There are two types of nozzles. One is called convergent nozzle. Another one is called as the convergent divergent nozzle. So when I am when the fluid is, for example, the steam, we are going to study only about steam here. So when the steam is allowed to pass through the nozzle here, so what will happen? So there will be a decrease in pressure. The pressure will be decreasing here, and then corresponding increase in velocity will be taking place in the case of a nozzle, because always pressure and velocity is inversely proportional. Both are energies. When I am trying to decrease the one form of energy, so automatically this will be converted into another form of energy. So preferably, so this will be in terms of a velocity. So always the pressure and velocity is inversely proportional. So what will be doing it? So when I am decreasing, when I am trying to decrease the pressure, so that will increase the velocity there. So in this way, by varying the cross section of the nozzle, by varying its flow passage, so we are increasing the velocity of the fluid which is passing through the nozzle. So that is the purpose of the nozzle. So whenever if I am using a nozzle there, so I will get a very high velocity, increased velocity at the output of a nozzle. So that is the purpose. If I want to use a nozzles, then ultimately I will be getting a high velocity fluid at the nozzles. That is the basic purpose of a nozzle. Then what about your convergent nozzle and divergent nozzle? So if I'm using a convergent nozzle there, so the gain in velocity relatively lower. If I'm using a convergent divergent nozzle, so the gain in velocity will be relatively higher. If I want to specifically say, there are two types of flow called subsonic flow and supersonic flow. This is about your aerodynamics part. So we might have something here about subsonic flights, supersonic flights and all. So subsonic and supersonic is based on the classification of a so-called non-dimensional number called Mach number. Mach number is again, this is defining the velocity of the fluid directly. So if the Mach number is less than 1, we'll call it as flow is subsonic flow. If the Mach number is greater than 1, the flow is supersonic flow. If the Mach number is equal to 1, we'll call it as a sonic flow. For example, if the Mach number is greater than 5, very, very high, then such flow is called a hypersonic flow. So we might have heard hypersonic rockets and supersonic rockets and all. So to define the velocity in terms of non-dimensional number, we use a Mach number here. Here we'll not be using, this is for a general specification. Coming to our convergent divergent nozzle, if I'm using a convergent nozzle, so I'll be getting a relatively lower velocity. That flow is the subsonic flow. If I'm using a convergent divergent nozzle, so I'll be getting a so-called supersonic velocity. So for that purpose only, we'll be using a convergent divergent nozzle. So if this is the plot which representing the variation of pressure and velocity along the length of the nozzle. So if I am allowing the fluid to expand through this nozzle here, so you are saying that this is the curve of a pressure. So there is a continuous decrease in pressure here and corresponding gain in velocity here. So in this way, so we'll be getting a increase in velocity when the fluid is allowed to expand through a nozzle. So such a device, so we are using in our steam power plants generally. Exactly where it will be used in the case of steam turbines. So the high pressure steam. High pressure means it will be low velocity only. So such a steam will be allowed to pass through a nozzles inside the steam turbines, not a single nozzle, because nozzle shape will be generally small. So you'll be having group of nozzles. Number of nozzles would have been placed inside the steam turbines. That when the steam is allowed to expand, so it will be coming out with very high velocity. So that high velocity is utilized to drive the steam turbines there. So that will be utilized to drive the steam turbines, so that we are getting a positive power output. So that is the one way. So in this way, so nozzles are being used in the steam power plant to obtain a very high velocity. This is all about the theoretical part about the nozzles there. Now coming to the some basic derivations with respect to the nozzles. First, we are going to get the very basic equation. Suppose if I want to know what would be if I'm allowing a steam to expand in a nozzle, then what would be the exit velocity if I want to calculate it. Accordingly only I can able to design the nozzle there. And then how I can calculate my exit velocity? For that I have to go back to my basic equations. From that, so I'll be trying to get my expression to calculate the exit velocity of the nozzle. Okay, for that, so we are going to use the first law of thermodynamics. So I think you might have studied your first law of thermodynamics. What it says that when I am supplying heat to a system, it will do some work. When I'm supplying heat to the system, it will do some work. Some energy will be stored in the system. So all the heat will not be converted into a work. Some heat will be stored, some energy will be stored in the system. That energy is called total energy. So that energy may comprises in the form of internal energy, partly in the form of potential energy, partly in the form of kinetic energy. Even we may have etc. We may have some other forms of energy will also be there. Okay, so whichever is significant, that we are considering it here. So the total energy here we need to consider, because steam possesses very high heat. So definitely internal energy will be there. Internal energy is nothing but some heat energy. So and then the actually potential energy will be negligible in the case of a nozzle, but we'll be still considering it. We'll be neglecting it later. And then so your kinetic energy is significant here, because the very important purpose of the nozzle itself to increase the velocity. So this has to be considered here. So in this way, we are going to use very basic equation, namely Q minus W equal to del E. We call it as a first law of thermodynamics to obtain the expression for velocity of a nozzle here. Now we are going to suitably substitute the Q, W and del E here, and then we'll proceed with that. And coming to our total energy here, total energy equal to, we have written it as internal energy and potential energy and kinetic energy sum. Now coming to this work done, generally if the work done is consider in the case of a flow device. We call it as a steady flow device. So what is steady flow device? Turbines, nozzles, heat exchangers, these are all called steady flow devices. So there will be a fluid which will be, it will have explicit inlet and outlet. Fluid will be flowing, continuously flowing and outlet. So that we can call it as a steady flow device. In this, the pressure and temperature, otherwise other parameters will be constant for a particular period of time at any point. For example, this point. So if I'm having some pressure and temperature, for example, if it is suppose if it is allowing, if the steam is allowed to expand in a turbine, a high pressure, high temperature steam. For example, if the pressure is around some 80 bar and temperature is 500 degrees Celsius here, assume that, and then it is allowed to expand. So when it is allowed to expand here, so here the temperature pressure may reduce this point. So maybe coming to around 60 bar and 400 degrees Celsius. Here again it may further reduce. But if I'm measuring at the second point, which is around 60 bar and 400 degrees at any point of time, for example, 5 minutes, after 5 minutes, same 60 bar and 400 degrees Celsius will be maintained. Even after 10 minutes, at this point, again same 60 bar and 400 degrees Celsius. Like that, at particular point, even if the time passes, but the properties are not changing. Such device is called steady flow devices. Okay, examples are, it may continuously vary at particular point. If I'm measuring here at any point of time, that will be same. Such device we call it as a steady flow devices. So your turbines and your nozzles, heat exchanger, compressor, all are steady flow devices, which is having explicit inlet and outlet. Okay. What is non-steady flow devices? For example, if we have a piston and cylinder arrangement, okay, I'm holding a which does not have inlet and outlet. I am just holding a gas inside this. I am giving some external heat. So because of the heat, you see that the gas may expand. It may push the piston down. Similarly, if I am contracting it, the piston may compress the gas. Like that, the gas volume will be same inside. It will not come out or it will not go inside. So such device is called non-steady flow device. Otherwise, closed system. So whenever we consider a work done in the case of a steady flow device, two types of work will be considered. One is called shaft work, another one is called flow work. So shaft work means, so you have a turbine, you take it, so when the steam is allowed to expand, so because of this steam energy is utilized, so I'll be getting some output. So that is shaft work. So what about flow work here? So if you see it here inside and outside, so this turbine, for example, if we take this as a turbine here, in this we may have opening inside for inlet and outlet. So the opening will be generally small considering your entire size of the turbine there. So what has to be done? The fluid will be offered some resistance to enter into this, because it is a hole is slightly smaller compared to your entire size of your turbine there. So it has to do some work to enter into this. Similarly, when it comes out, so it is a large area, it is coming out through a small area. It has to do some work here. So that work is called flow work. The fluid will be offered some resistance. The fluid, it has to overcome this resistance to enter and to come out from the device. So such work is called flow work here. So the PV is nothing but, you see that if you substitute the units, pressure is Newton per meter square, and this is your volume. So volume is metric cube. If you tally with the unit, you will get Newton meter. P into V is Newton meter. Newton meter is work done. So that's why we use P into V here. So the difference between outlet and inlet, we call it as a flow work here. Flow work is nothing but the resistance offered to the fluid to enter and leave. Okay, so the fluid has to do some work. Otherwise, it has to overcome the resistance offered to enter or leave the system there. That work is called flow work. This is not applicable if the fluid is not there. Okay, so whenever you have a fluid system is there, so two types of work we'll consider. One is called shaft work and flow work. So that we will call it as a work done. So that I am going to substitute it in this expression 1 in addition to the total energy. So Q I will keep as it is. Q I will keep as it is, and then this W is sum of shaft work and flow work. So that I'm writing it as shaft work plus P2 V2 minus P1 V1 here. And This is generally the first law says that this is change in total energy, correct? Not total energy, change in total energy. So it is final minus initial. So correspondingly, if I'm writing this as E2 minus E1, that is change in final energy minus initial energy, correspondingly this right hand side should also be written in the same way. In this way, so your total change in energy can be written it as U2 minus U1 plus mg is going to be constant, and Z2 minus Z1 plus of m V2 square minus V1 square. Mass is going to be constant here. So we'll write in terms of final minus initial there. Now we have the expression for del E and W in suitable form. So that has to be substituted in equation 1 here. So 2 and 3 have to be substituted here. If we do it if we substitute in that, then we'll get the expression Q minus. So you have minus here. So minus will be multiplied here. So minus WS, and this again here you have plus, minus into plus minus. So minus P2 V2 minus into minus plus. So plus P1 V1. So right hand side term we'll write as it is. Now we have to further simplify. Okay, our basic idea is to obtain the velocity of the steam, final velocity V2. Expression for V2 we need to get it now. Okay, that is our aim in our discussion now. So let this will be the equation now. Now coming to the nozzle diagram here. So this is a convergent divergent nozzle. So you have an inlet and outlet, and then you have a reference line here, otherwise datum line. So if I'm measuring the distance from the reference line 1 and 2, so that I will call it as a Z1 and Z2. Basically, in the case of nozzles and all, so your inlet and outlet will be positioned in the same place. So in that case, the change in potential energy will be 0. Suppose if the inlet and outlet is changing, for example, if we take this one, inlet and outlet is changing. If I'm drawing a reference line here, if I'm measuring 1 and 2, definitely Z1 will not be equal to Z2. In that case, change in potential energy will be considered. This will be significant there. But in the case of a nozzle, so the diagram, it is very clear that Z1 is approximately equal to Z2. So it will not be varying. So Z2 minus Z1 will be equal to 0. So change in potential energy is 0 in our equation. So this will become 0. Next, coming to the other parameters here. So already we have discussed that if I am allowing the steam to expand in the nozzle, because of the change in cross section only, we are getting an increase in velocity. We are not doing any work on the steam. Simply we are allowing because of the change in cross section. So we are getting a change in velocity there. So we are not doing any shaft work. Shaft work is possible only in the case of a turbine and a compressor. So we don't have any shaft here. So obviously your WS, shaft torque, will be 0 here. And then coming to our heat transfer part. Heat transfer, this is Q is nothing but heat interaction of steam to the surroundings. So actually if we see that, so steam is high temperature steam, maybe around we have some 300-400 degrees Celsius steam will be coming into this. So actually there will be some heat loss will be there to the surroundings. By considering the velocity change here, it will be coming very fastly and it will be leaving it. Here the velocity and pressure change is significant in the case of a nozzle. So what we'll do it for the simplicity, so we'll assume the heat loss is small amount. So we cannot say it as exactly 0, it is a small amount. So in that case, so the heat interaction, the heat loss will be negligible. So such a device, in that such a assumption, we call it as a adiabatic device. That's why I put this symbol here. So it is adiabatic. So the heat loss is minimum or negligible. So we'll reduce the Q equal to 0. If I'm carrying out my Q, nothing wrong in that, definitely you'll get a very accurate answer. But if I'm carrying out this Q, this additional term will lead to the complication while doing analysis. Since the amount is very small, the heat loss is very small there, because it will be quickly going, because the velocity is increasing there. So it will be going out very fastly. The loss will be minimum, so that we are neglecting the heat transfer here. So Q will be 0 here. So if I am substituting these assumptions in our expression, Q is 0, WS is 0, and mz z2 minus z1 is 0. So the rest of the term I'll put it here. So I'm putting it in that way. So I'm what I will do it here. So I'll p1 v1. So I kept p1 v1 here, and then I'll bring this minus u1 on the left hand side. So p1 v1 plus u1 minus p2 v2. I'll bring it on the right hand side. Rest of the terms we'll write as it is. So if we do it so, then we'll have the expression p1 v1 plus u1 equal to p2 v2 plus u2 plus of m v2 square minus v1 square here. Now we know that in our thermodynamics, enthalpy equal to U plus PV. So that is internal sum of internal energy and pressure volume product. That only we call it as an enthalpy. So this U plus PV can be directly replaced with H. If I'm writing capital H, it is called enthalpy. If I'm dividing this capital H by M, this is called as specific enthalpy. So enthalpy per unit mass. So we used to refer with small letters. For example, V, volume, I'm dividing by M, meter cube per kg, small v, specific volume. So like that, any extensive properties can be divided by its mass, it will become an intensive property, it will be referred with its corresponding lowercase letter. Capital E, energy, dividing by M, small e, specific energy. So like that, in our thermodynamics and thermal engineering and all. So this is the practice. Capital letters, so we'll be specifying dividing by its M. Only extensive property only will be divided. Pressure, temperature cannot that those are all intensive properties. So those properties cannot be divided. Okay. So in this way, I can divide this entire expression after substituting my U plus PV here. So I'll write it. I'll divide by M here. So if I'm dividing by M, so H, capital H by small m is specific enthalpy. This is enthalpy. Similarly, you have small h, that is on exit on the right hand side. V2 square minus V1 square. So m gets cancelled. So of V2 square minus V1 square here. So I will keep our enthalpy on the one side and velocity term on the other side. So if we do it so, then we'll have of V2 square minus V1 square equal to H1 minus H2 here. And then I'll bring this off on the right hand side, so that this will be 2 into H1 minus H2. On the left hand side, we'll have V2 square minus V1 square here. So actually we need an expression for exit velocity V2. So I'll keep V2, rest of the terms I'll write on the right hand side. So that V2 square equal to 2 into H1 minus H2 plus V1 square. So we need only V2. So this is V2 square. So we will take a square root on both sides. If I am taking square root, this V2 square will become V2 because it is V2 square whole power 1 by 2. So 2 and 2 gets cancelled. So I will get only V2. So this square root will take this term here, root of 2 into H1 minus H2 plus V1 square. And then this is the expression for to calculate the exit velocity of a steam nozzles here. Sometimes considering the exit velocity, inlet velocity will be very small amount. Sometimes in our problems, they may be asking us to ignore the inlet velocity. For example, inlet velocity may be some 10-20 meters per second. So exit velocity goes up to 90, 100, 110 meters per second. So it is very high comparing to inlet velocity. So if inlet velocity is very small amount, sometimes we'll neglect it. If we're neglecting it, so our expression is going to be V2 equal to root of 2 into H1 minus H2. So from this, what we have understood, so it is very clear that because of your enthalpy drop, enthalpy is nothing but some heat energy. Heat is nothing but again energy. So by the heat energy is converted into velocity gain. So the heat energy, we are expending the heat energy in the nozzles. That heat energy is converted into a velocity gain. Okay, so the steam is very hot. The heat energy is used for increasing the velocity in the nozzle. So from this, we are getting we are getting this information very clearly. Okay, so this is very important expression. Okay, so we are going to use in our problems. And then coming to another small derivation, continuity equation. So in our fluid mechanics, we have studied continuity equation. Continuity equation says that your discharge remains constant. Discharge means what? Volume flow rate. Flow rate per unit time. that is based on the law of conservation of mass. Whenever a fluid is allowed to flow through a device, its mass flow rate will remain same. Velocity may change. The fluid will readjust itself to maintain the mass flow rate. Mass flow rate and volume flow rate, discharge all are same. Okay, mass flow rate, volume flow rate, discharge all are same. Only unit is different. Mass flow rate is, it will be in kg per second. Volume flow rate and discharge is in meter cube per second. So that is in terms of volume, that is in terms of mass there. So based on the continuity equation, always your mass flow rate or volume flow rate or discharge will remains constant. Okay, so that relation will be used to calculate the mass flow rate in the case of a nozzles there. So this mass flow rate can be defined with respect to the relation density of the fluid, cross-sectional area of the passage, and then velocity of the fluid, rho A B. So density we can use the your unit as kg per meter cube, and flow area meter square, and velocity is meters per second. So if you simplify the units here, meter square and meter cube. So meter cube gets cancelled. So kg per second. So mass flow rate unit is kg per second. Now this mass flow rate, this density and all will be using for incompressible fluids. Okay. So generally when we use steam and vapors, even we might have observed in our steam tables, we never use the density. Inverse of density is specific volume. So we might have seen in our steam tables, we are using V, specific volume, H and S, VF, VG, HF, HFG. So that column was there. So whenever we use a steam there, instead of, it is preferable to use density instead of, it is preferable to use specific volume instead of density. So that we use it, we will take inverse of density as the specific volume. So instead of density, we'll use specific volume in the case of a nozzle. So this equation can be rewritten as area into velocity by 1 by specific volume. That is nothing but your rho there. So your specific volume unit is meter cube per kg. Density unit is kg per meter cube. So always we use a dry steam. We'll use VG here. We never use a wet steam or already we have seen F, G and G. G refers, now Rankine cycle we have seen. This is nothing but completely gaseous form, pure steam. So that's why we use G, because we use steam nozzles here. Otherwise, simply we use V. So this refers, A is the cross-section area of the nozzle, and V is the velocity of the steam, and small v is the small vg is the specific volume of the steam. Since your mass flow rate remains constant, we can write m dot equal to constant. That we can write it as A1 V1 by Vg1 equal to A2 V2 Vg2. So these two equations, mass flow rate and our velocity at exit, these two equations are very important. So this will be used to calculate the steam properties in the while we are designing the nozzles. Okay, so I hope you understood this theoretical part and also the derivations. So you please copy this one, copy பண்ணிக்கங்க. So after that we'll go to the next one. Okay, இன்னைக்கு எவ்வளவு இருக்கீங்க? 14 இருக்கீங்களா? காப்பி பண்ணிக்கிறீங்களாமா? ஓகே சார். So we have successfully completed
one doubt, sir.
சொல்லுங்கம்மா. Yes.
Sir, actually we are using nozzle. We are using for high velocity only. Correct, sir?
Yeah.
For high velocity convergent nozzle is okay. Because the front side only velocity will be increased automatically. Then yes. Divergent nozzle, how to increase the velocity, sir?
Yes, very good question. Okay, so I will answer for you. So if you see it here, so this is your convergent nozzle. So if pressure is decreasing and velocity is increasing. Okay, so that's correct. You agree with that? So you have a convergent nozzle, and then here the area is increasing, correct? Okay.
Yes, sir.
So the area is increasing here. So obviously what has to be done here, the velocity is increasing, mean here the velocity has to decrease, correct? Okay, so but the velocity is increasing. Okay, so what is the reason for that? What Gurudev Pandeva, question asked by Gurudev Pandey. Okay.
Yes, sir. How? Sir.
Yes, okay, I will answer for you. So for this, you need little more explanation. I will answer for you. Okay. Okay. Now, uh, I was telling you the velocity is increasing in the convergent part, and also so this curve clearly shows that pressure is decreasing, correct? And then
Yes, sir.
correspondingly velocity is increasing. So by when the shape is changing, it has to decrease here, but it is not happening. Velocity is increasing there. See, there are two parameters hmm, which involve the increase in velocity. One is the inlet conditions, okay, inlet conditions, and then so-called pressure ratio and mass flow rate. Inlet condition is the first part. Mass flow rate and pressure ratio. A proper mass flow rate and pressure ratio has to be maintained. Otherwise, what will happen? Instead of increase in velocity, there will be a decrease in velocity in the divergent part. Okay, not only the change in cross section is influencing, some other parameters also influencing. Okay, what I will do, I'll give another example. Okay, so that you'll understand. So you all about a vapor compression refrigeration system. You have studied in our diploma, I think. Vapor compression refrigeration system. Have you studied?
I
No.
studied, sir, but I did not
Forgot.
remember.
Okay. I'll make you to remember. Now I'll Google out. Huh? I'll Google out. I'll show you. Don't worry. I'll clear your doubt, my dear friend. Okay. I'll write vapor compression refrigeration system. Okay. 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 Can you able to see this image, my dear friends?
Yes, sir.
Okay. I'll take another diagram. Okay. So I'll take this diagram. This diagram is visible. Visible or comma? Others also, please. Okay. So if you take your vapor compression system, vapor compression system, first of all all our refrigerators are working on vapor compression system. Your split AC, your domestic refrigerator, your car AC, everything is working on vapor compression refrigeration system. Very, very efficient system. It consists of basically four components: compressor, condenser, expansion valve, and evaporator. Correct? Without which the system will not work. We may have some additional equipments maybe there, but without this the system will not work. So what is happening? We need to understand this working, okay, so that I can correlate this one with our nozzles now. So in our vapor compression system, diagram clear irukkalama? In the diagram, is it visible? Okay, so
Yes,
that
sir.
Yes, sir. Yes, sir.
yes.
Visual.
Okay, good. So now in this vapor compression system, basically we'll be using a refrigerant. We colloquially we call it as a gas, filling gas, like that we'll call. That is nothing but refrigerant. There are various kinds of refrigerant, so that we are using it. So exactly what is happening inside the system. So you have it is again it is cyclic process. So you have a vapor refrigerant will be coming out from the evaporator. It is entering into the compressor here. So we run the compressor and will increase the pressure and temperature of the refrigerant in the gaseous form. So high pressure, high temperature refrigerant in vapor form, it is coming out. It is passing through the condenser. So when it comes through the condenser, we use some external arrangement, external cooling fan or something like that. We convert vapor refrigerant into liquid refrigerant here. Okay, we extract heat from that. Phase change is taking place. So vapor refrigerant is converted into liquid refrigerant, theoretically constant pressure. Okay, so already it is a high pressure, high temperature vapor refrigerant. It is coming down. We are just cooling it, converting vapor refrigerant into liquid refrigerant. The pressure remains same. There will be small pressure drop here. So again, it is called as they are saying it as high pressure side. Okay, you call. So this is a high pressure liquid refrigerant. It is coming here. Coming to the this is called expansion valve or throttle valve. So how do you what is expansion valve? What is throttle valve? The expansion valve is nothing but you assume we have a tap in our home. Okay, tap is 90% closed. Tap is 90% closed. Just a 10% opening is there. So it is restricted passage. Your tap, I have closed 90%. I open a small opening. I am allowing a fluid over there. In that way, you assume as the expansion valve, very small diameter tube. So in that, the high pressure fluid should pass through. High pressure refrigerant should pass through here in a very, very small diameter tube, that only we call it as a expansion valve or throttle valve. Okay, now what is happening when the high pressure refrigerant is passing through this, it will undergo a huge pressure drop. So pressure and temperature is directly proportional. So there will be a huge temperature drop. So what will happen? So here there will be a very low temperature liquid refrigerant will be coming. So when it is a low temperature liquid refrigerant, so it is a cooling effect. Immediately we are getting a cooling effect here. This cooling effect, we are cold refrigerant we are allowing in the evaporator. So that what evaporator is our freezer box. Okay, so cold refrigerant is passing through this. Whatever the load we keep it here, it will absorb the heat so that it is passing through this. So in this way, our vapor compression system is working now. Now coming to this now, so we were discussing that high pressure liquid refrigerant is passing. Okay, so it undergo a huge pressure drop. It is coming out as a low pressure refrigerant. In that way only we are getting a cooling effect here. Okay, so it is happening actually. Now you see here, high pressure liquid refrigerant, it is passing through a very small, here the diameter is large, it is diameter is small. Okay, exactly what should happen? Gurudev Pandey, can you answer me for this? If I am saying high pressure, I am allowing through a small passage, what will happen? Larger diameter to smaller diameter, what will happen exactly? High pressure, further pressure has to increase, correct, Amma? Gurudev Pandey? High pressure
Yes,
means,
sir.
again, if I am passing a small pressure, pressure has to increase, correct? But what is
Yes.
happening here? Pressure is dropping. So they are written very clearly, high pressure side, low pressure side. So there will be a huge pressure drop here. But actually, what should happen? Pressure has to increase further, but this will not take place. Because of the drop in pressure only, temperature is dropping, we are getting a cooling effect. That is a refrigerating effect. This is practically happening in all the refrigerator. We are achieving the cooling effect here. So now we have some questions here. Now you see it here. If it is a low pressure refrigerant, if it comes through this, exactly what will happen? Because of this small diameter pipe, actually pressure will increase. Correct, Amma? If it is a low, and assume that instead of we have a low pressure liquid, okay, assume that low pressure refrigerant is coming. If it is small diameter tube, pressure will increase. This will become high pressure. Correct? Do you agree this?
Agree, sir.
Low pressure means pressure will increase. High pressure, so obviously the pressure is decreasing. That means, so we need to understand not only this change in cross section is also important, the inlet condition is also important. Okay, so for example, nozzle is to increase the velocity, decrease the pressure, otherwise decrease the pressure. Okay, so now if I am allowing a low pressure steam here, what will happen here? The
High.
pressure will, yeah, so pressure will high means velocity will decrease. So nozzle is serving the purpose of increasing the velocity, that is decreasing the pressure. Then I need to allow here low velocity, high pressure. So that is very important here. So that means not only the your area is, otherwise the flow path is important, the inlet condition is also important. If I am allowing a low pressure, low pressure steam here, instead of increase in velocity, there will be decrease in velocity. Okay, so this is the one point. And then I was telling you about mass flow rate and pressure ratio. For that, this is second thing you should understand, then only it will be justified. Okay, Gurudev Pandey. So for that, I'll give another example. Okay, after that we correlate these two. Okay, so I'll open for you another. Okay. 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 So actually, this is all about, this is something about regarding our aerodynamics part, but we can correlate here. You see it here. You have a convergent divergent nozzle. Okay, you have a convergent divergent nozzle. You have a throat here. Throat is nothing but the junction of convergent and divergent, we call it. Okay. So here they have done an experiment. Okay, what experiment? Where convergent and divergent nozzle has been connected with the a reservoir, a tank, and then inlet. Outlet is connected with a collecting tank.
We call it as an exhaust chamber. This is visible, Amma? Is it visible?
Yes, sir.
Friends? Yes, good. Okay. Now, here they have done an experiment. What experiment they have done? It means initially they have provided with a wall, the opening and closing wall they have provided here. First, the wall is completely closed. Valve is completely closed means the stored liquid, whatever it is compressible, so you have a vapor, so it will not flow, it will be stagnant. So when I'm slowly opening this, so the flow will take place. When the flow is taking place, you see that they observed the pressure variation along the nozzle. You have a convergent shape, you have a divergent shape here. Okay, so they obtained the different curves here. So you see so for a one position of valve, just slowly slightly opened in the way you can assume. So there is a decrease in pressure, correct? Up to this decrease in pressure. So that means increase in velocity, because pressure and velocity is inversely proportional. So there is a decrease in pressure, so corresponding increase in velocity. So after that, the divergent part, what has happened? Pressure is increasing, correct? Pressure is increasing. So that means velocity is decreasing. In this, velocity is decreasing in the divergent part. For another position of a valve, so there is a further decrease in pressure, that is corresponding increase in velocity. After that, again the pressure is increasing. Instead of decrease in pressure in the divergent part, pressure is increasing. Pressure should not increase in the nozzle. If it is increasing, the nozzle will not serve its purpose. We will get a decreased velocity. Okay. So and then again you see the curve C. So here the pressure is decreasing. Okay, good. We are getting a velocity increase. Here the pressure is increasing, not correct. Next curve coming to D. So we have up to this increase in decrease in pressure. Okay, good. Velocity is increasing. After that, pressure is increasing. Like that, you see it A, B, C, D, E, F, G, and I, J. All the curves are not showing the purpose of the nozzle. If you come to your curve H, so I'm just seeing this curve here. Okay, this is the curve. Okay, for one position, you see that the velocity, pressure is decreasing up to the throat, that is Mach number equal to 1, sonic. After that, the Mach number is greater than 1. What is happening? The pressure is decreasing, correct? So the pressure is decreasing means velocity is increasing. So at only one curve is showing the purpose of a nozzle. So the velocities keep on increasing till at the end. I mean pressure is decreasing, so that you are getting increased velocity. So how it may happen in a single nozzle, how these conditions may happen. So they are varying the pressure for a various position of the valve. So it has happened. Varying the position means I am varying the pressure. So if I am that is called pressure ratio, inlet and outlet pressure. Okay, so if I have the inlet pressure is constant, I am varying the outlet pressure. If I am putting P2 by P1, that is PE by P0, that is called pressure ratio, and then I need to maintain particular mass flow rate in that. So for a particular mass flow rate and pressure only, so the nozzle will do its purpose. Otherwise, if I am not maintaining that mass flow rate and pressure ratio here, so that the nozzle will not do its purpose. Instead of that increase in velocity, the decrease in velocity will be taking place. How to find out that? So we need to do some analysis, and we need to have some experimental parameters. Based on that, we need to find out that exact mass flow rate and pressure ratio, then only we'll get the increased velocity. So the nozzle, so that is the state called nozzle design condition. If the nozzles are operating in this condition, that is called off design condition, OFF, off design. So the nozzle should not be designed to operate on this. Nozzle has to be designed to operate only to get a curve of H here. Only to get a curve of H here. Then only so we'll be getting. So there are two parameters we need to understand. One is which is our vapor compression system. From this, what we understood, not only the flow area, inlet condition is very important. Okay, second point here, so we need to maintain some mass flow rate and pressure ratio, then only the nozzle will serve its purpose. Otherwise, so we'll not get increased velocity in the divergent part, only we'll get a velocity only in the increase in velocity convergent part. Okay, so you see it here. So we are getting a Mach number less than 1 here, subsonic, so supersonic. supersonic velocity, we are getting a divergent part here. So if I'm using a divergent nozzle, I'll be getting a Mach number greater than 1. That is called the supersonic velocity. I hope I have answered you. Okay. So by just saying that, so we cannot understand that it is opposite direction. So velocity is increasing or decreasing, but we have to closely look into that. So we have to consider all these parameters so that we can understand. Okay. So it's a very good question. Okay. So I answered for you. Even I can show from this book. I think your doubt is clear, my dear friends.
Yes, sir. Are
Very
you telling, sir?
yes, sir.
There are some ratio will be fixed, pressure and velocity in inside, sir.
Yeah. For that, yeah, particular mass
If
flow
that
rate and
ratio
pressure
is
ratio, we have to
not
design.
follow means we can't get
Yeah,
that velocity, sir.
yeah.
Am I right, sir?
Yeah, exactly. Very good, very good. Even you see that even in our rockets, we are using convergent divergent also. Rocket is used to get a very high velocity. The same book I'll show you that. Okay. So we have this is with respect to a book on something regarding aerodynamics. Okay, I'll show you. So that even if you see the convergent divergent shape in our nozzle design. Okay. So that so yes, சொல்லுங்கம்மா yes please.
மேக் நம்பர்னு சொன்னீங்களா?
ஆமாம்மா மேக் நம்பர் எஸ்.
அப்படின்னா என்ன சார்?
மேக் நம்பர் நாமா மேக் நம்பர் என்னன்னா இட் இஸ் த ரேஷியோ ஆஃப் வெலாசிட்டி ஆஃப் த ஃப்ளூயிட் டு த வெலாசிட்டி ஆஃப் சவுண்ட். அந்த ஃப்ளூயிட்னுடைய வெலாசிட்டி வந்து நான் டைமென்ஷனல் பண்றதுக்காக என்ன பண்றோம்னா அந்த மேக் நம்பர் அப்படிங்கறத வந்து டைரக்ட்லி இட் இஸ் ஃப்ளூயிட் வெலாசிட்டி தான். நம்ம வந்து ரெப்ரசன்டேஷன் ஷுட் பி ஈஸி. ஸோ அதுக்காக என்ன பண்றோம்னா அந்த மேக் நம்பர் அப்படிங்கிற டேர்ம் வந்து வில் யூஸ் இட். இந்த புக்லேயே கூட அது இருக்கு, நான் ஷோ யூ. ஸோ ஆக்சுவலாக இன்ஜினியரிங் அனாலிசிஸ்லாம் வந்து என்ன பண்ணுவோம் அப்படின்னா we used to refer with some non-dimensional numbers, so that is easy representation. அதுக்காக வந்து we use that. It is the ratio of velocity of the fluid to the velocity of sound. Velocity of sound will be always constant. அது வந்து acoustic velocity physicsல படிச்சிருப்போம். அது வந்து denominatorல கான்ஸ்டன்டா இருக்கும். fluidனுடைய velocity மாறும்போது so a Mach number will be varying. Okay, so I can show you here. So if you see in our it is one of a liquid propellant rocket. You see this convergent divergent nozzle. So if suppose if the velocity is decreasing in the divergent nozzle, they will not use this. So the velocity has to increase because we need a very high velocity. Correspondingly, we will get a thrust force. So that only used to give a propelling the nozzle. So you have a convergent divergent nozzle there. Okay, there is another diagram. So you see it here, a convergent divergent nozzle. So you get a very high velocity here. So it's very important thing, and also the inlet condition. Okay, so I think I answered for your question. So I am happy that I cleared your doubt. Okay, Gurudev Pandey, my dear friend. Okay, okay, ma'am. Now you please copy it. If you are just seeing that one, so it is very difficult to understand how velocity will increase in both in convergent and divergent part. But these parameters should be considered for a nozzle. Okay, copy பண்ணிக்கிறீங்களாமா? There is another device called diffuser. So that is opposite to that nozzle. So diffuser is nozzle is used to increase the velocity. Diffuser, the similar shape will have it. That we'll call it as a diffuser. So that is used to increase the pressure. If I am allowing a low velocity fluid, this entire shape will act as a nozzle. It will increase the velocity. If I am using a high velocity fluid, the same device will act as a diffuser. So it will give it will decrease its velocity. So same device will act as a nozzle and will act as a diffuser. Even diffuser is used in some of the applications. So we need to understand that the inlet condition is very important, and we need to maintain a particular mass flow rate and pressure ratio to get the increased velocity at the even part of the nozzle.
சார்
எஸ்மா எஸ்
நமக்கு
ப்ளீஸ்.
கன்வர்ஜன் ஆசிட்லயே நமக்கு வெலாசிட்டி அதிகமா தானே சார் இருக்கும் கன்வர்ஜன் ஆசிட்.
இல்லம்மா கன்வர்ஜன் நாட்ஸ் இல்ல. இது வெலாசிட்டி அதிகமா தான் இருக்கும். பட் நாட் ஈக்குவல் டு த டைவர்ஜன். இது வந்து என்ன டைவர்ஜன் டெவலப் பண்ணா ஃபர்தரா இன்க்ரீஸ் ஆகும். ஸோ இது அந்த புக்ல காமிச்சிடலாமா? அந்த கவ் இன்க்ரீஸ் ஆகுது இல்லையா மேக் நம்பர். அந்த கவ்ல வரும்போது பாத்தீங்கன்னா மேக் நம்பர் லெஸ் தென் 1 திருப்பி வந்து மேக் நம்பர் கிரேட்டர் தென் 1 ஆகுது. ஸோ அப்போ டைவர்ஜன் பார்ட் யூஸ் பண்ணாதான் வில் கெட் ஏ இன்க்ரீஸ்ட் வெலாசிட்டி ஃபர்தர். இங்க திருப்பி கன்வர்ஜென்ட் யூஸ் பண்ணா அந்த மாதிரி கிடைக்காது. ஸோ யூர் ஆஸ்கிங் தட் இன்னும் கன்வர்ஜென்ட் பண்ணா யூர் ஆஸ்கிங் தட் மோர் வெலாசிட்டி அப்படி கிடையாது ஆக்சுவலா. ஓகே ஸோ இட் ஹாஸ் டு பி டைவர்ஜென்ட் தர். அந்த இப்போ நான் காமிச்சேன் ஒரு பிக் டயக்ராம் வேரியஸ் கவ்ஸ். அந்த கவ்ஸ்ல பாத்தீங்கன்னா ஸோ இந்த த்ரோட்டுக்கு அப்புறம் இட் இஸ் கம்மிங் m கிரேட்டர் தென் 1 சூப்பர்சோனிக் கிடைக்குது. ஸோ தட் இஸ் பாசிபிள் ஒன்லி த டைவர்ஜென்ட் ஷேப். Those things have been found only experimentally, so that's why we are using that one.
அந்த த்ரோட்டுக்கு அப்புறம் வந்து உள்ள இன்டர்னல் கன்ஸ்ட்ரக்ஷன் வேற மாதிரி இருக்குமா இல்ல இதே மாதிரி தான் இருக்குமா சார்?
இல்ல இதே மாதிரி தான் நார்மல் தான். வேற சிம்பிளி இட் இஸ் ஏ கன்வர்ஜன் அண்ட் டைவர்ஜன் பேசேஜ். ஃப்ரீதா தான் இருக்கும், ஸ்மூத்தா தான் இருக்கும் பேசேஜ், வேற எதுவும் இருக்காது அது. ஓகே வெறும் நோ மேஜிக்லாம் ஒண்ணு இல்லம்மா. இப்ப நான் சொன்ன மாதிரி தான். ஓகே அந்த 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 இதை பாத்தீங்கன்னா டயக்ராம் பண்ணி காமிச்சேன் இல்லையா? ஸோ அந்த கர்வ்ஸ் பாத்தீங்கன்னா வேரியஸ் கர்வ்ஸ் அது எக்ஸ்பெரிமெண்டலா ட்ரா பண்ண கர்வ் அது. ஸோ இந்த கர்வுமே மேட்ச் ஆகல. ஒன்லி ஒன் கர்வ் இஸ் மேட்சிங் வித் தட் இஸ் த கர்வ் H. So that is they are getting increased velocity.
இல்ல ஆக்சுவலா க்ளோசர் பார்ட்ல இருந்து ஓபன் பார்ட்டுக்கு வரும்போது வெலாசிட்டி கம்மியா தானே சார் ஆகும்?
எங்கம்மா இதுலயா? இந்த பார்ட்லயா? அதான் இப்ப நான் பார்த்தேன். அதான் நான் சொன்னேன் இல்லையா? இது ஓபன் தட். ஓகே
புரியுது நான் பார்த்தேன். ஆக்சுவலா பிராக்டிகலா பார்க்கும்போது நமக்கு வந்து அந்த மாதிரி தான் தோணுது.
அந்த கர்வே பிராக்டிகல் தான் மை டியர் ஃப்ரெண்ட். ஓகே அந்த கர்வே பிராக்டிகலுக்கு தான் அது. ஓகேவா? அதாவது என்னன்னா இப்ப நம்ம தியரிட்டிக்கலா பார்க்கும்போது தான் அது தெரியுமே தவிர பிராக்டிகலா we are getting in that பிராக்டிகலா டிரா பண்ண கர்வ் அது. ஓகே
சார்.
ஓகே that's why I was showing you the example. ஈசக் இருக்காரா? ஈசக் தானே இருக்காராமா இல்லையா?
இல்ல சார்.
Yeah. So last week I came to Apollo. தெரியும்லமா உங்களுக்கு? லாஸ்ட் வீக் ரெண்டு மட்டும் தான் பார்த்தேன், வேற யாரையுமே பார்க்கல. என்ன இது ஃபீட்பேக் கேட்டிருந்தாங்களா உங்ககிட்ட?
ஆமா சார்.
ஓகே என்ன நல்லவர் வல்லவர்னு சொல்லிட்டீங்களா?
உங்களுக்கு தான் அதிகமான ஓட்டு.
அப்படியா? இல்ல அதாவது இது எப்படின்னா டீச்சிங் மெத்தடாலஜி ஒருத்தர் ஒரு ஸ்ட்ராட்டஜி ஃபாலோ பண்ணுவாங்கம்மா. அது வந்து அவங்களுக்கு பெஸ்டா இருக்கும். பட் அது நம்ம இது பண்ண முடியாது. என்ன மாதிரி வேற அப்போ வேற ஸ்டூடெண்ட்ஸும் இது பண்ணாங்களோ? ஆன்லைன் மாதிரி ஏதாவது பண்ணாங்களா? எப்படி பண்ணாங்க?
இல்ல ஆன்லைன் இல்ல சார். ஜஸ்ட் என்கிட்ட ஒபினியன் கேட்டாங்க.
ஜஸ்ட் ஃபீட்பேக் தான் சார்.
மீட்டிங் மட்டும் போட்டு ஒபினியன் மாதிரி கேட்டாங்க. மீட்டிங்
ஒபினியன் மாதிரி கேட்டாங்க.
ஓகே அவர் சதீஷாமா அவங்க ஹெச்ஆர்? அவர் அவங்க ஹெச்ஆர்டிம்ல இருக்காரோ சதீஷா?
ஆமா சார், சதீஷ் குமார் மோகன்.
அவர்தான் ரைட். அவர்தான் ரிசீவ் பண்ணிட்டு போனாரு பார்த்தேன்.
ஓகே
அந்த நாசல் கீழ ஒரு கிராஃப் மாதிரி இருக்குல்ல சார், அது ஃபுல்லா காமி சார்.
ஆமாமா இந்த கிராஃப் வந்து வேரியேஷன் ஆஃப் பிரஷர் அண்ட் வெலாசிட்டி அலாங் தி லென்த். இந்த மட்டும் காப்பி பண்ணிக்கலாம். அங்க வந்து உங்களை பத்தி வந்து ரொம்ப பெருமையா சொன்னாங்க கம்பெனில. நீங்கெல்லாம் வந்து நல்லா டெடிகேட்டடா ஒர்க் பண்றீங்க. ஷிஃப்ட் எல்லாம் உங்களுக்குள்ளேயே வந்து நீங்க வந்து அட்ஜஸ்ட் பண்ணிக்கிறீங்க. அப்படியா? உங்களுக்குள்ளேயே மியூச்சுவலா அட்ஜஸ்ட் பண்ணிக்கிறீங்களாமா ஷிஃப்ட் எல்லாம் டைமிங் கிளாஸஸ் அந்த மாதிரி? அப்படியா?
ஒரு சில டிபார்ட்மெண்ட்ல வந்துட்டு அவங்களே ஷிஃப்ட் அரேஞ்ச் பண்ணிடுவாங்க.
ஓகே
டிபார்ட்மெண்ட்ல அந்த மாதிரி பண்ண முடியாது. பசங்களுக்குள்ள அவங்க மாத்துவாங்க. அதுதான் கொஞ்சம் கஷ்டம்.
கரெக்ட்மா. மியூச்சுவலா நீங்களே வந்து மேனேஜ் பண்ணிக்கிறீங்க. சில டைம் வந்து கண்டினியூஸ் அப்படியே ஷிஃப்ட்டை கண்டினியூ பண்ற மாதிரி இருக்கும். கரெக்டாமா? ஸோ அதெல்லாம் ரொம்ப கஷ்டம் இல்ல? ஓகே பரவாயில்ல. ஸோ டெஃபினெட்லி ஸோ யாரு நீங்க ரொம்ப ஹார்ட் ஒர்க் பண்றீங்க.
கஷ்டம் சார்.
எதுமா வாய்ஸ் பிரேக் ஆகுது.
நைட் ஷிஃப்ட் போயிட்டு திரும்ப அடுத்த நாள் கண்டினியூ பண்ண காலேஜ் பண்ணிட்டு திரும்ப நைட் ஷிஃப்ட் போறது தான் கஷ்டம்.
ஆமா சார், நைட் ஷிஃப்ட் டைம் தான் ரொம்ப டிஃபிகல்ட்டா இருக்கும். மத்தபடி ஓகேவா தான்.
ஓகே ரொம்ப பரவாயில்ல, ரொம்ப கஷ்டம் தான். பரவாயில்லமா. ஸோ டெஃபினட்டா நீங்க இவ்வளவு கஷ்டப்பட்டு யூ ஆர் கோயிங் டு கெட் யுவர் டிகிரி. ஸோ டெஃபினெட்லி
சார் now a little bit okay sir, night shift time, but call is going and return coming in 9:15 to 9:30, room reach. After just eating and prepare press and going to again night shift.
Also you have to wash your clothes also.
Okay. Oh, so it is very difficult.
Now online class for night shift little bit relaxation sir.
Oh, so coming to college and going, so
more than 2 hours extra sleeping sir.
Yeah,
tired,
sir. Yeah. So online class will be better for you, so that you can have some relax, correct?
Yes sir, 2 hours extra sleeping. That's
okay. Very good. Anyway ma, so you are putting your physical effort, you are trying to get your degree, so definitely that will give credit. Okay, உங்க B டிகிரிக்கு நிறைய வேல்யூ இருக்கு. அதனால வந்து நீங்க கஷ்டப்படுறதெல்லாம் வீண் போகாது. ஓகே, அதனால வந்து நீங்க அதனால worry பண்ணிக்காதீங்க. The end of your course you will get a fruit. அது வந்து டெஃபினட்டா உங்க லைஃப் லாங் நீங்க வந்து நல்ல பொசிஷன் போலாம். ஸோ யுவர் வில் ஹேவ் சேலரி ஹைக், ப்ரமோஷன் எல்லாம் நல்லா இருக்கும். ஸோ பி டிகிரிங்கிறது அவ்வளோ ஈஸி கிடையாது. ஸோ இன்ஜினியரிங் டிகிரி ஸோ டிஃபிகல்ட் டு கெட், ஸோ தட் யூ ஆர் அச்சீவிங் ஈவன் parallel you are working and you are getting it, so definitely it is very valuable. Okay, அதனால வந்து very small suffer a short period, so definitely will have a good credit after some time. Okay, நான் ஜார்ஜ் என்ன ஆன்சரே வரல ஒன்றும். ஜார்ஜ் ரெப்ரசன்டேட்டிவ் எதுவும் சொல்ல மாட்டேங்கிறாரு. ஜார்ஜ் இருக்காரா இல்லையா?
ஆமா சார், உண்மைதான் சார்.
ஓகே இது காப்பி பண்ணும்போது டவுட் இருந்தா சொல்லுமா. வேற ஹேவ் யூ ஸ்டேட்? எல்லாம் கம்பெனி நியர்பைல இருக்கீங்களாமா இல்ல வேற லாங்ல இருக்கீங்களா? வேற ஹேவ் யூ ஸ்டேட்? எங்க நியர்பையா லாங்ல இருக்கீங்களா? எல்லாம் அந்த வெஸ்தாம்பரம் சைடுல தான் இருக்கீங்களா இல்ல வேற இடத்துல இருக்கீங்களா?
எஸ்பி கோயில்
ஒருத்தரும் ஒரு இடத்துல இருக்காங்க சார்.
எஸ்பி கோயிலா? எஸ்பி கோயில்ல இருந்து எப்படிமா வர்றது? அங்க இருந்து வர்றது ரொம்ப கஷ்டமா இருக்கு. சிங்கப்பெருமாள் கோயில்ல இருந்து வருவீங்க, ரொம்ப லாங் இல்ல. நியர்பைனா ஈஸியா இருக்கலாமா? வெஸ்தாம்பரமா அந்த படப்பை அந்த மாதிரிலாம் கொஞ்சம் ஈஸியா இருக்கும்.
ஆமா
சார் படப்பை
Yeah, Padappai means it will be easy for you.
ஒவ்வொருத்தரும் ஒவ்வொரு இடத்துல இருக்காங்க சார்.
அப்படியா? ஓகே. So WS is shaft work and WF is flow work. வெதர் தே ஆர் சப்போர்ட்டிங் ஃபார் ஃபீக்லாம் ஏதாவது சப்போர்ட் பண்ணுவாங்களாமா கம்பெனியில், அதர்வைஸ் யூ ஹேவ் டு பே, அந்த மாதிரி ஏதாவது இருக்கா? ஃபீ பேமெண்ட்லாம் ஏதாவது சப்போர்ட் பண்ணுவாங்களா? அதர்வைஸ் யூ ஆர் பே ஒன்லி அவங்க
ஆமா சார்.
ஸ்பான்சர்ஷிப் மட்டும்தான்.
75% வந்துட்டு
75% கம்பெனில இருந்து ஸ்பான்சர் பண்றாங்க சார். 25% நாங்க பே பண்றோம்.
அதுக்கப்புறம் வந்துட்டு பாண்டிங் இருக்கும் சார், 3 years பாண்டிங்.
பாண்ட் இருக்கும். ஆமா, ஜெனரலா
ஆமா,
ஆஃப்டர் கம்ப்ளீட்டிங் கோர்ஸ் கம்ப்ளீட் அப்புறம் 3 இயர்ஸ் நீங்க ஒர்க் பண்ணலாம் இல்லையா?
ஆமா சார்.
ஆமா சார்.
ஓகே ஓகே ஓகே, பரவாயில்ல, குட்.
சார் அந்த லாஸ்ட் லைன்ல ஈக்குவல் டுக்கு அப்புறம் U2 மைனஸ் U1 சார்?
இல்ல, ஆமாமா, கேபிட்டல் U2. U வந்து U தான், அது இன்டர்னல் எனர்ஜி, இந்த U அது வந்து U.
U2 மைனஸ் U1 கரெக்டா சார்?
ஆமாமா, U2 மைனஸ் தான், கேபிட்டல் U2 மைனஸ் கேபிட்டல் U1.
ஓகே சார்.
அது V மாதிரி தெரியுதுல்ல? சரி, ஓகே.
ஆமா.
U தான், U தான். இது முடிச்சிட்டீங்கன்னு நினைக்கிறேன். I'll go to next page.
சார் லைட்டா டவுன் பண்ணுங்க சார். தப்பா
So the diagram ஒரு நிமிஷம் காமிங்க சார்.
Diagram, okay.
டயக்ராம் போடல கொஞ்சம் லைட்டா
முடிக்கலையா? ஓகே.
டவுன் பண்ணுங்க சார்.
சார் அந்த H is equal to H/m இருக்குல்ல,
ஆமாம்மா,
அது கொஞ்சம் எக்ஸ்பிளைன் பண்ணுங்களேன்.
அதாம்மா. அதாவது தெர்மோடைனமிக்ஸ்ல வந்து ரெண்டு ப்ராப்பர்ட்டி இருக்கு, இன்டென்சிவ் ப்ராப்பர்ட்டி, எக்ஸ்டென்சிவ் ப்ராப்பர்ட்டி. இன்டென்சிவ் ப்ராப்பர்ட்டினா இண்டிபெண்ட் ஆஃப் இட்ஸ் மாஸ், எக்ஸ்டென்சிவ் ப்ராப்பர்ட்டினா டிபெண்ட் ஆன் இட்ஸ் மாஸ். ஸோ அந்த எக்ஸ்டென்சிவ் ப்ராப்பர்ட்டி எல்லாமே வந்து மாஸால டிவைட் பண்ணலாம். ஸோ அந்த எக்ஸ்டென்சிவ் ப்ராப்பர்ட்டி இப்போ இது ஒர்க்கு, ஹீட்டு, எனர்ஜி, இதெல்லாமே வால்யூம், இதெல்லாம் எக்ஸ்டென்சிவ் ப்ராப்பர்ட்டி. அதை மாஸால டிவைட் பண்ணால் ஸோ அது வந்து இன்டென்சிவ் ப்ராப்பர்ட்டி ஆயிடும். அது எப்படி நம்ம ஸ்பெசிஃபை பண்ணுவோம் அப்படின்னா, ஹவு டு யூ ஸ்பெசிஃபை மீன்ஸ், ஸோ our extensive property will be specified with its capital letter H. So by mass. So H is enthalpy, joules, dividing by its mass, kg. So joules per kg. So if you are dividing by m, so that will take the word of specific. Enthalpy will become specific enthalpy. For example, volume, ரொம்ப familiar, volume capital V by m. Volume is metric cube by m power metric cube per kg. So volume dividing by its mass, it becomes specific. So specific volume, small v. So small v equal to capital V by m metric cube per kg. So like that, any extensive property can be divided by its mass. So that will be referred with its corresponding lowercase letter, capital E, G. அதை எம்ஆல் டிவைட் பண்ணா ஸ்மால் இ ஆயிரும். எனர்ஜி வந்து ஸ்பெசிபிக் எனர்ஜின்னு சொல்லுவோம். அந்த மாதிரி நம்ம தெர்மல்ல அந்த மாதிரி டெர்மினாலஜி யூஸ் பண்ணுவோம். ஸோ அதாம்மா அந்த எக்ஸ்பிளனேஷன். ஓகே
ஓகே சார்.
சார்
yes.
இந்த V1 நெக்லிபிள் பண்ணிருக்கீங்களா, எதுக்கு சார்?
அதாம்மா, அதாவது எப்படின்னா, இது ஆக்சுவலா இதுதான் ஆக்சுவல் டெரிவேஷன், V2 ஈக்குவல் டு இந்த டேர்ம். சில நேரத்தில் என்ன ஆகும்னா V1 ரொம்ப கம்மியா இருக்கும். ஆக்சுவலா எக்ஸிட் வெலாசிட்டி தான் நாசில் ரொம்ப அதிகம். எக்ஸிட் வெலாசிட்டி கம்பேர் பண்ணும்போது இன்லெட் வெலாசிட்டி வந்து கம்மியா இருக்கும். அப்போ சில டைம் என்ன பண்ண, சிம்பிளிட்டிக்காக வந்து சம் ஆஃப் த ப்ராப்ளம்ஸ் they will be asking us to inlet velocity, they will not give it. கண்டுபிடிக்க முடியாது. சம்டைம் they'll be asking us to neglect the inlet velocity. அப்போ நெக்லெக்ட் பண்ண சொல்லிடுவாங்க. ஸோ அந்த கேஸ்ல வந்து இட் இஸ் நாட் ஜீரோன்னு எடுக்காம நெக்லிஜிபிள் அமௌண்ட், மேபி 10-12 மீட்டர்ஸ் பர் செகண்ட் இருக்கும். நமக்கு கெயின் பார்த்தீங்கன்னா 110-120 மீட்டர்ஸ் பர் செகண்ட் வரும். அதை கம்பேர் பண்ணும்போது ரொம்ப ரொம்ப கம்மி. ஸோ இன் தட் கேஸ், ஸோ யூஸ்வலி we used to neglect the inlet velocity in the case of a nozzle, because low velocity fluid only will be coming into the nozzle as we have seen. ஸோ அதனால வந்து நெக்லெக்ட் பண்ணும்போது ஈக்குவேஷன் யூனிஃபை ஆகும் அதுக்காக. பட் ரிசல்ட் வில் நாட் பி அஃபெக்டட் மச் as velocity value is very very less. Even if I am using this is also correct. ரெண்டு ஈக்குவேஷனுமே யூஸ் பண்ணலாம். ஓகே, ஈக்குவேஷனை சிம்பிளிஃபை பண்றதுக்காக இது
எழுதியாச்சு சார்.
அடுத்து இது காப்பி பண்ணிட்டுங்க. தட் வில் ஃபினிஷ் அவர் கிளாஸ்.
சார் ரைட் பண்ணல சார், லைட்டா மேல போங்க சார்.
கண்டினியூட்டி ஈக்குவேஷன் மாஸ் ஃப்ளோ ரேட் இங்க வந்து m டாட் அப்படின்னு யூஸ் பண்ணுங்கம்மா. ஜென்ரலா வந்து m யூஸ் பண்ணா அதுக்கு பேரு மாஸ், அது வந்து சாலிடுக்கு யூஸ் பண்ணுவோம். whenever யூஸ் ஃபார் fluid அது வந்து ஃப்ளோ ரேட் ஆயிடும். அப்போ m ன்னு யூஸ் பண்ணா சாலிடுக்கு, m டாட் யூஸ் பண்ணா fluidக்கு. அதுக்காக வந்து யூஸ் m டாட். m டாட் ரெஃபர்ஸ் மாஸ் ஃப்ளோ ரேட். சிம்பிளி m போட்டா அது என்ன ஆயிடும்னா மாஸ் சாலிட ரெஃபர் பண்ற மாதிரி ஆயிடும். fluid வரும்போது m டாட் அப்படின்னு யூஸ் பண்ணுவோம். mass flow rate m dot equal to constant. This is kg per meter cube, meter square and meters per second. So meter square and meter cube cancelled. So we will have kg per second.
சார் அந்த 1/v வந்துட்டு ரோவா சார்?
ஆமாம்மா, டென்சிட்டி இஸ் இன்வர்ஸ் ஆஃப் ஸ்பெசிஃபிக் வால்யூம். இது வந்து ரிலேஷன்.
ஓகே சார். அது ரோ தானா சார்?
ஆமா, ரோ தான்மா.
ஓகே சார்.
ஓகேம்மா, முடிச்சிட்டா சொல்லுங்க. I'll take attendance.
Complete, sir.
Okay.
Sir, 1 minute. Okay, sir.